So this talk will be about navigating the future, leveraging large language models for autonomous driving. Before I go into the technical details, let me first give you some overview about what Bosch is doing. So you might know Bosch from your washing machine or from your laundry machine, but there's actually much more to that. So Bosch is a huge company. We have around 400,000 employees in total, and our business can be divided into 4 sectors. So we have mobility solutions, which would include autonomous driving, industrial technology, energy and building technology, and consumer goods. Now, if we go one level deeper and look into our research setup, then we have around 2,000 colleagues that are working in research. And as you can see here on this map, we are spread all over the world. So we have colleagues working in the States, in Asia, and also in Europe. Our main hub is in Germany, in Renningen. That's also where I'm located. You might not know Renningen. It's rather small, so it has about 20,000 inhabitants, but it's very close to Stuttgart. So how are we doing research-wise? Here you can see our publications in 2021. So it's all good, I would say. So we are located in here. If we would now update this slide and look into this year, into 2023, I think the picture would still roughly be the same. Now, let's start with the technical content. What will we discuss today? So I will first give you a very brief overview over the rise of large language models. I think most of you all know that. Then I will connect large language models to autonomous driving, first on a more of a highlight level, but then I will also give you a deep dive. And in this deep dive, I will talk about our paper, Can You Text What Is Happening? Pre-trained language encoders for trajectory prediction models. Afterwards, I will conclude and give an outlook. So let's start with the large language models. I think in Europe, this workshop, I don't have to talk too much about it, but there's really a buzz going on about generative AI and large language models. So here I collected a few headlines over the last few months that I think give a good overview of what is happening right now. If you read the first one, it says Unleashing Economic Growth, How Generative AI is Shaping the Future of Prosperity. So this basically means that really there's AI and large language models now really enter the market to the business sectors. Second one is the hottest new programming language is English. I also like this one. It basically more or less says, why should I care to program if I have ChatGPT and Copilot, right? Third one is it may be that today's large neural networks are slightly conscious. This one I find very interesting because it's still for me an open point on how large language models really work. So it's not clear how much do they understand or how much do they only learn by heart what they see during training. And the last one is chatbots might hallucinate more often than many realize. And this basically points to one of the open problems that we still have. And that is if you use a large language model and you somehow get it to be outside of the training data, then it starts doing things that one cannot expect. So if we think about how did we get to this point, I think it makes sense to have a brief look at the history of artificial intelligence. So we can start with machine learning, where the first steps, I think, were taken around 1950, and then the first bigger round was around 1990. And here we basically had more or less simple models like neural networks, Gaussian processes, or support vector machines that worked in low-dimensional spaces. Still, there was like a big difference between these machine learning methods and standard physical methods that people have been applying before, because here you had now an algorithm or a method that could be reused for different problems across domains. Then the next big step was taken in around 2020, when the era of deep learning started. Here, it was a technical invention that made a big change to go from machine learning to deep learning. And this technical invention was basically the invention of GPUs that allowed us to progress neural networks more efficiently, and this allowed us to go to deeper networks. And this also allowed us basically to scale up to more high-dimensional inputs, like for instance, images and texts. And now we are in the era of large language models, where models have again increased in size. The size of the training data sets has again increased, and both together now leads to new models that have a much better understanding of what is going on in the world than the models we had before. So how do these models work? Here's one example task that one can do with a large language model. The task here is to fill in the missing word of a sentence. So here I also have an example sentence that is autonomous vehicles offer a rich source of high-impact research problems for the ... community, including trajectory prediction models. So what we can now do is we can take the sentence and feed it into a large language model. And what we get out is basically a distribution over words for the missing word. And here we can, for instance, see that a good words that get a high probability are scientific community, research community, and so on. Now, later in our deep dive, we will have a look. We will use one specific language model, and that is BERT. BERT is or was invented 2018, so it belongs to the first generation of language models, but it's still in use. We can now spell it out. So what does it stand for? It's bidirectional encoder representations for transformers. And I will now basically step by step explain what the different words are, since these are the different components of the model. The first one is bidirectional. And this basically means that BERT reads a sentence from left to right, but also from right to left. So if it looks at a word, it takes into account the context coming from before the word and also after the word. This is a big difference to standard generative models, because if you want to generate text, you only can read from left to right, but you don't know yet what's coming on the right side. And if your goal is not to generate new text, but basically to have an understanding of a given text, this can, like having like a bidirectional reading, can give you more expressive power. Then the second part is encoder representation. This basically means, what does BERT do? So it takes a sentence, then it takes the sentence and splits the words into tokens. And then the encoder, what it does is basically for each token, it learns a latent representation. For pre-training, it here uses two tasks. The first one is masked language modeling. This is what we just saw on the other slide. And the other one is next sentence prediction. But afterwards, one can also use the BERT encoder for different tasks. This is also something that we will see later on in our example. Then the last word is transformer. So here, basically, this is the model architecture our model is built on. In each transformer in the transformer, we have basically a number of different layers, and most importantly, we have the attention layer, which allows information flow between the tokens. Now, why is this model still important? So we used not BERT, but distal BERT in our experiments, and it's still kind of small compared to more modern language models. And this allowed us to do fine-tuning on a single GPU, which made our life much easier. Now, if we look on how are large language models used today, then we have a couple of very well-known applications, like chatbots, language translation, software development, or educational apps. If we now look at these applications, then what we can observe is that all of these applications have in common that the input is already text. And that makes it very easy for the large language model to work on these problems, because the input already has the correct format. And the big question now that we have to pose ourselves in autonomous driving is basically how can we use these models for tasks which are not natively expressed in text. And this is what we will talk next about. So how can we connect large language models with autonomous driving? So here's a switch in gears, basically. Now we change perspective from large language models to autonomous driving. And in autonomous driving, we basically have 4 standard applications for AI. So we have simulation, we have perception, behavior prediction, and control. In simulation, our goal basically is to test models in a virtual environment. In perception, we want to make sense out of sensor data. Behavior prediction has as goal to predict the behavior of surrounding traffic agents. And in control, we want to make decisions for maneuvers. And now if we think about these 4 applications, then they all come with data sets where these models are trained, and these data sets are recorded with sensors. That means our raw data is cameras or it's LiDAR data. Maybe we also have GPS data, but we don't have text. And so the question is, how can we use large language models that are primarily designed to process text for these different tasks? And I will now basically give you 4 applications where one would like to use large language models, and where also like first papers have come out that go in this direction, and then I will deep dive into one of those. So first one is simulation. What here one would like to do is to generate targeted scenes. That means basically I can say to the generator, please create me a scene where 2 cars are crashing. Now this would be very easy if we would already have a paired data set with scenes and annotation. As long as we do not have that, one thing that we can do is, for instance, that we create synthetic prompts out of the scene description and then feed them into a large language model. Second thing is perception. So here the goal would be quite similar. It would be basically that we want to retrieve scenes for LiDAR data. Now, here we have the same problem that we do not have a data set that is matching LiDAR data with text. But what we can now do is we can basically use images as a bridge. And that means there exists data sets where LiDAR data is paired with images, and there exists also data sets where images are paired with text. And for the second part, so for image text pairings, we also have, for instance, clip models. And now what we can do is basically we can use image as a bridge to also connect image LiDAR with text. And this then also allows us to query LiDAR data efficiently. The next application is trajectory prediction. And here, what we would like to do is we would like to augment the inputs by a text description in order to increase the performance. I will go into more details about this application in a minute. And last but not least, we have control, where one goal could be to include a text narrative to the output. So for instance, the car does an action, but it also says why it does this. This can help a lot when we think about explainability or interpretability. And here we also have an example where a paired data set is given that makes it possible to learn such a model. So what I will do next is basically I will give you more details into the behavior prediction example. And this is also, you can read it up in our paper, pre-trained language encoders for trajectory prediction models. This is joint work with Ali, Andreas, Ethan, Ronche, Jörg, and you. And here we worked on the new scenes prediction challenge, where the goal is to predict future XY trajectories of neighboring traffic participants of a given scene. So what we basically want to do is Given the surroundings of the last few seconds, we want to predict what a neighboring car is doing in 5 seconds. And our idea here was to augment the input with text descriptions that can then be combined with a pre-trained language encoder. Before I describe the model, I will describe you the base model we are building on, and this is CoverNet. We use CoverNet as a baseline because in the new scenes dev kit, there is also an implementation of CoverNet available, and we were building on this one. So what CoverNet does is it uses an encoder-decoder architecture to solve the problem. And for this, it first takes the input and it represents the input as a rasterized image. This is what you can see here. And then it takes this image and encodes it with a convolutional neural network and concatenates some features. This latent representation is then fed into a decoder, which predicts a potential trajectory. What is a bit of a special case of CoverNet is that it treats the prediction problem as a classification problem. So that means it has a predefined set of trajectories, and for each of these trajectories, it predicts a probability that this is the next trajectory. Now, what we do is rather simple. We basically augment this model with a second input modality that takes text as input. So this is what you can see here. So we first have a text prompt. I will show you in a bit more detail how it looks like in the next slide. And then we feed this prompt into a language encoder. Then we concatenate both latent representations and give them to the decoder. So you might wonder how we learn this model. And here we also use a very simple way of doing it. So we first basically fine-tune the vision encoder on the training dataset in isolation, then the language encoder in isolation, and then we freeze the weights and relearn the decoder in the last step. For the vision encoder and the language encoder, we built in pre-trained models from Hugging Face. And here you can now also see how our prompt does look like. So it first tells the large language model that it's an expert for self-driving cars. Then it describes the task, and gives information about the context and the lane. So here it gives information about speed, acceleration, and the positions over the last meters. And here we have information about the lane. Note here that we only give information about the state of the agent and the lanes, but not about the neighboring agents. So this is much less information that we normally give the model. And now here you can see our results. So first we use a vision encoder only. The original paper used CoverNet, so these are these numbers here in the first blue line. And now we basically, in the first step, we only replaced the vision encoder by a more modern architecture. And by doing that, we could already improve performance. Then in the next step, we used the text encoder only. And you can now see that our results are a bit worse than if we use the transformer-based vision encoder by B, but still they are kind of good. So they are still better than the original CoverNet implementation. And I think this is already kind of amazing because we use here much less information than we use in CoverNet. For instance, like the neighboring agents do not enter in our model. Then last but not least, we combine the information from the image and the text encoder. This is what you can see here. And you can see that if we combine both encoders, that we can improve our performance. That basically means that both encoders complement each other and capture different information. So what did we do in this paper? We basically did a proof of concept. So we showed that different modalities complement each other well and that their combination has superior performance. However, so here I want to be also honest with you, our model did not achieve state-of-the-art performance yet. For doing this, further refinements would be necessary. Now, what could we do in order to boost our performance? One thing is scale is everything. So we used in our model the byte model, which is rather small. But what we have seen in the last years is basically that every time we make a model bigger, we get a better performance. And so we think that this is the same, would also hold true for our model, and that our performance would improve if we would use a bigger model. Another thing is that, as I just explained to you, we fuse rather late, and we could also use a joint encoder that jointly learns a latent representation over text and images. If we would do this, we could also capture intermodal relationships, and this could improve our feature representations. So now let me also give you a bit of a more general outlook what to expect for the field of autonomous driving when we combine it with large language models. So I would say what we see at the moment is really only the beginning. So there will be a lot of more and new and exciting possibilities come up for autonomous driving when we get deeper into the connection between large language models, foundation models, and also generative AI. Now, why should we care? Why should we incorporate large language models into autonomous driving? One thing is that large language models have the potential to increase the interpretability and the explainability of AI solutions. So if at some point in the future we could make a prediction and then we could ask the model, why do you predict this? This would help us a lot for interpretability. The second thing is incorporating large language model into AI reasoning systems can improve the reasoning capabilities, since the large language model has a vast amount of open world knowledge. So what do I mean by this? For instance, if we think about a large language model, it does already know that a car does only go forwards on a highway. This is something that is included after pre-training, while if we learn a model from scratch, it does not know this. And then the last point is, still there is some research to be done in order to include large language models in autonomous driving. One point is that if we look at current architectures, then they have a significant computational demand. And this can be a limiting factor if we think about resource-constrained environments, like, for instance, embedded systems and autonomous driving. Yeah, and that's already it. So I try to save some time in between. But if you have questions, I'm very happy to take them now.
All right, yeah, we have some questions. Yeah, anyone.
Hi, sorry, a quick question. Any ideas why your model did not achieve the state-of-the-art areas of potential improvement that you think the future can achieve state-of-the-art?
So, I mean, one reason, that I did not talk about it, but which could be a reason, is, for instance, that we use this classification decoder. And many of the more modern architectures also use different decoders. And it could also be that our performance would improve if we change the decoder, for example. Also, what we could also try and did not do yet is basically to combine our large language model with a GNN encoder. That could also be a direction going forward.
I want to ask you, what do you think is the benefit of the multimodality of the model?
So you basically mean what do we gain by including the large language model?
Yes. And
So
do
I
you
think
do you have a shared latent space then?
no, we don't have a shared latent space since we only concatenate the two. It's more that I think that both encoders can capture different things, and if we basically include information from both sides, we know more than only knowing one of the two. And now, if you ask me what do I think that the large language model can bring to the overall model, then I think it is this open world knowledge on which it is pre-trained. So it basically it has a much stronger prior than the vision encoder. Because if you think about, that I think would be the most benefit, the main
So
benefit.
you have the agents and the ego and whatnot on the visuals, and then you discretize the space and build the language decoder. And then you concatenate the two strings together, the visual embedding and the and
Exactly.
you wanna use the how do you want to use the CNN on the language?
No, I don't. So I
The
don't
CNN
use.
encoder.
So I use the CNN encoder on the image, and I use the language encoder on the text, and then I get two latent representations, and then I concatenate them.
Okay, you have then two shared latent representations, and so you will work with the features on the visual side, and then okay, thanks a lot.
Okay, yeah. So basically, I concatenate both set of latent features, and then I have like a decoder afterwards. And the decoder afterwards basically then merges the features from the two different representations.
Okay, I do have the one more question though.
Sure.
When you say it's not state of the art, what is the state of the art? What would you point out as the state of the art today?
Okay. So so here I think you caught me, but basically if you look at new scenes, then what you can do is you can look on the leaderboard, which you will find online, and then the numbers that are reported by MinADE, I think they are around 1.2, for instance, and we are at 1.87. So there's still a gap in performance if we compare our models with the models from the leaderboard.
Good. Thank you so much. Thanks for the presentation.
I can be far away from the speaker. Hi, Barbara. Thank you for your talk. I have a question about applicability of LLMs on board. I think like everybody knows that the LLMs are not only enormous in their size, but which is much more important, that they require autoregressive decoding procedure, sequential. And this is like what blocks from deploying them on board. So what do you think, like, what do we really need? And is there any opportunity to put LLMs on board, and what are the options? Thanks.
What do you mean exactly by autoregressive in this part?
For example, when we need to provide the, I don't know, the path, the route, for example, for the next 5 or 10 seconds, you need to decode token by token, and like every new like input requires even more latency.
But this is the same for every model, right? So this is not, I mean, it's a bit worse for the LLM because it's so expensive, but this is something that I need to do for every model. Maybe I can,
Okay. I'm asking about decoders, like GPT-X, for example. Yeah.
Yeah, so, okay. So I think what in general must be done, so I think there are two ways on how to go. Basically, one way is that one distills the model and gets it smaller, but then you must do a lot of distill work. The other thing one could think of is basically if it's possible to find a cloud solution where the computations are not done in the embedded system.
I see. So cloud solution. Okay, thank you.
Thank you.
Do we have any questions on the Zoom Q&A? No?
Barbara, can I also ask another question about like sources of data for snippets of language that might be useful for tasks like this? Where to find them? Because I guess like for a lot of different types of driving, there usually isn't a lot of text on the internet about how people are, maybe making the decisions they're making, or like why they would choose certain decisions. Actually, at Toyota, we tried this, and we would get people to describe how they were making their decisions as they were driving, but we found it was really hard to collect the data because it's a huge cognitive load to ask someone not just to demonstrate driving, but to consciously verbalize why they're making the decisions they're making as they're driving. And so these people would come back very mentally fatigued. And we found we could only collect a tiny amount of data this way. Do you think there's like how do you view, if you're to scale up approaches like this, like where the main source of data could come from for like, meaningful driving decision making?
Yeah, so I think this is something that really is an open question to the complete field, right? Like how to get these paired data. There are, like you said, you tried it out. Also, there's this one public data set, BDDX, which is a paired data set, but I also think it will be very difficult to scale this up to the amount of data that is usually used for training an autonomous driving system, because they're really like hundreds and hundreds of, very, very large amounts of data are needed. Like, I think one can, it's good to have a data set like this, but it will never be the complete data set. And what we did is like creating the synthetic prompts. This is basically something that is very cheap to do, because therefore we don't need human annotations. So I also like, if you use human images as a bridge, this is also something that is very cheap to do. So I think basically maybe a combination of both is the way to go forward, like having a cheap data, which you can have like large amounts of, and then a bit of more expensive data that really has the properties that you like to have. And if you think about other applications, this is also often done, right? That you try to get cheap and much, and then maybe a smaller data set which has some special properties that are difficult to get.
Okay, yeah, thanks, Barbara. That makes a lot of sense. And actually, one follow-up question, if I may. One of the things I've always wondered is like, humans speak languages, and if we've got an autonomous vehicle, there's probably a customer in the car. If it's a human-driven taxi or something like that, they can often ask the human to do different things, stop or go slower, or like pull over to the side or something like that. Do you think there's any scope here to, do you think kind of, using what you presented, there's a natural way to get the customer to interface with the decision-making procedure as well, to maybe impart preferences or anything like that to the reasoning that the machine is, using to come up with certain motions?
So I think that would be a really cool way to go forward, and also to personalize the driving experience, right? Because, for instance, if you think if you have a baby on board, then you might want to go slower. Like if you go out in the evening or something like this. I mean, everything, of course, still within the traffic rules, but still, some people like it if you accelerate fast. Others don't like it. So I think there's room for it. So in our application, we did not go in here yet. But if you think about, for instance, like this targeted simulation, where you also want to have a targeted scene generation, here you basically, you want to steer with text how a scene looks like. And I guess in a similar way, you could also do it in behavior prediction, that you also use text in order to, not for behavior prediction, but you cannot do it for the other cars. But if you want to control it, then I think this would also be something that is possible.
Great, thanks so much.